All right, last one. Let's do this. And this one again is going to be one of those little combined ones. So I have to prove that RZ, which is this line at the bottom, is congruent to YU, which is actually a little bit overlapping. Um, that goes to the end. So again, I'm asked to prove sides are congruent, but I think the only way I'm going to be able to do that is to prove that I actually have congruent triangles. And so again, what I mean is if that I can prove that this green triangle, the one I'm hastily shading in with this green highlight, if I can prove that this triangle is congruent to this one that I'm now shading in red, the side lengths that are part of those triangles would have to be congruent. And that's because corresponding parts of congruent triangles are congruent. That's the definition of congruent triangles. If I have all pieces in one triangle congruent to the other, they're congruent. And so backwards, if the triangles are congruent, then all their pieces have to be. So again, to prove congruency, I'm gonna actually, or to prove side lengths are congruent, I'm actually still gonna have to prove triangles are congruent. Can you believe that? So check this out. We still have our options open: side, 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 angle, angle, side, angle, side, angle, and of course my favorite, side, angle, side. So now we need to take stock of what information we've actually been given, and we've actually been given quite a bit. I do have a side in both red and green. I'll call them side 1, that are just given to us to be congruent. Now we have to be careful here. We have these two angles 5 and 6. They're not exactly given to be congruent, but ultimately they will be because they're both right. And so all I need to find is another side or another angle. Well, the bottom is going to be a bust because RZ and UY are going to be no good to me simply because those are the things I'm trying to prove. Like if you look, RZ and YU are right here. We don't know they're congruent. We're trying to prove them congruent. So I can't use side angle side. So side angle side is going to be out, and of course angle side 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 is simply because we've been given information about an angle. But I do think I have a chance to prove angle side angle. So let's kind of get close here. So I have this side, which I'm kind of making squiggly. I have this angle. So if I can prove this one, which I'm going to temporarily mark as 2, with these 2 tick marks, or these 2 arc marks, excuse me, is congruent to this one over here, I'm in business because that would give me side angle, angle, and of course angle, angle, side for the other one is for the green triangle as well. So the question is, well, how can I even do that? And it turns out I can, because again, let's kind of get close here. I know that I have this angle 4, which is congruent to this angle 3. But look, both 3 and 4 form a pair of linear angles with 1 and 2. And since 3 or 4 are the same, 1 and 2 have to be. Now that's going to be a little bit messy, but that's ultimately what I'm going to be able to do to prove angle, angle, side. Or side angle, whatever you want to call it. So anyway, let's go ahead and set up our proof. We're going to prove red and green are congruent, therefore the pieces have to be. So let's do this. So we have side 1, let's say angle 1 and angle 2. Let's go over there. Okay, so side 1 is going to be the easy one. We have SR congruent to TU because that's going to be given to us. There, fair enough. Angle 1, which is my right angles, is going to be a little bit different. It's not direct because we have to make sure we're maintaining the chain of logic. I do have that angle 5 and that angle 6 are right angles. And we can go ahead and justify that because it's given to us. Because it's marked in the diagram, it is considered a given. Okay. Well, if 5 and 6 are right angles, it's reasonable to say that the measurement of angle 5 and the went too fast there. The measurement of angle 5 is equal to 90 in the same way that the measurement of angle 6 is equal to 90. But wait a minute, if they're both equal to 90 by the definition of right angles, I could reasonably conclude from that that the measurement of angle 5 is equal to the measurement of angle 6. Because they're both equal to 90, they should be equal to each other. That is a classic transition move. And if they're both equal to each other, that would tell me that angle 5 is congruent to angle 6 because of the definition of congruency. Okay, which ultimately, what I wanted, angle 1 is now congruent as well. So I have one side length that's proven congruent, one angle is proven congruent, Now, let's get into angle 2. Now, this one's going to be the bear because I have to prove 1 and 2 are congruent, but I have to show they have the same measurement first. And it looks like I'm going to use some level of linear pairs as well, so check out how we're going to do this. Just to make it easier to see, I'm going to change colors and make it blue. So first I'm going to use my givens. I know angle 3 is congruent to angle 4 because it's given to me. It's not told, but it's actually marked in the diagram right here. Because angle 3 and angle 4 are congruent, I know the measure of angle 3 is equal to the measure of angle 4. Now that kind of dead ends right there, which is okay. I might use that information a little bit later. So let's kind of restart. We need 1 and 2 together in equations. So we need to write them into the proof. And the way I'm going to do that is by mentioning that angle 1 uh, and angle 3 and angle 2, angle 4 are supplementary. I'm going to abbreviate. And the reason I know that is because of the linear pair postulate, LPP. Remember, linear pair postulate says that if I have angles that are together and form a line, and they both are, that they are by definition supplementary. Okay, so we'll check this out. If I know 1 and 3 are supplementary, I know that the measure of angle 3 plus the measure of angle 1 is equal to 180. And also that the measure of angle 2 plus the measure of angle 4 is equal to 180 degrees. And the reason I know that is because that's precisely what it means to be supplementary. So the definition of supplementary. Okay, but now look, if the measure of angle 1 plus the measure of angle 3 is equal to 180, and so is a measure of angle 2 plus a measure of angle 4, I can reasonably conclude, and I'm going to jog my proof over here, I can reasonably conclude that the measure of angle 3 plus the measure of angle 1 is equal to the measure of angle 2. Oh, let me move that over a little bit. Oh god, I love Digilink. Plus a measure of angle 4. And how I conclude that is because of transition. So what I mean by transition is that I have 3 plus 1 is 180. 2 plus 4 is 180, so therefore I can cut out 180 completely, and those pieces are just all equal to each other. So let's go back and review this little blue piece that I said initially, but then kind of went away from. Um, 3 and 4 are given to be congruent, therefore they're equal. But look, now I have 3 and 4 right here, which means they're going to be a little bit interchangeable. So really, if I combine this piece and this piece together, I can actually say that the measure of angle 3 plus a measure of angle 1 equals a measure of angle 2 plus a measure of angle 3. And before you freak out and be like, oh, Mr. Collins, you messed up, it should have been a 4, I'm using actually substitution. Up here it says that 3 and 4 are the same angle, so I'm going to take out 4 and replace it with 3. That's going to be substitution. So if I know all these measurements are the same, I can subtract 3 off from both sides and say that the measure of 1 is equal to the measure of angle 2, and that's because of solving, like algebraic solving or simplification. And if the measurements are the same, good lord, look how long it took us to get here. If the measurements are the same, then angle 1 should be congruent to angle 2, which is exactly what we needed to happen. Angle 1 and angle 2, which are right here, they are congruent because of the definition of congruency, which means I have side angle angle. So if I start combining my pieces together, whoa, what's going on? I just messed something up. I don't even know what I just did. This is crazy. Nothing apparently. What's that? I didn't do anything, yet it had to wait. If I combine these pieces together, I can actually conclude my triangles are now congruent. I can say triangle, I don't know, SZR is congruent to triangle, so SZR, the red triangle, TYU because of side angle angle triangle congruence. And if those are congruent, then good lord, we are done. RZ has to be congruent to YU because of CPCTC. And that is actually where we end, which kind of gives you a sense why I like flow proofs, because even if I run out of room, I can just keep on going. So all this proof says down here is what we knew from the very beginning. If I want to prove RZ along the bottom is congruent to YU along the bottom, I have to prove the triangles are congruent. I did that by using side angle angle. Side 1 is given to us. Side 2 were ultimately congruent because they're both right angles. And then, I'm sorry, angle 2. And then the third angle, I had to use kind of linear pairs and a bunch of substitution to accomplish that. But I did. It took quite a few steps, but it's actually there. If the triangles are congruent, which I'll rewrite that for the key. If the triangles are congruent, then that means my side lengths have to be. Boom goes the dynamite. This one is in the books. I think we got one more left.